So far, we've only encountered three really simple equations to think about motion in one dimension. But there's a whole set of equations that we can use to solve different types of problems. And that set of equations we call the kinematic equations. Kinematic essentially means motion. So here are the equations we will be using for one-dimensional motion with constant acceleration. These are in your textbook, equations 2.50 all the way to 2.54. So we use these for, yes, constant acceleration. So here, for example, this first equation, here we have our x position. This is our final x position, if there's no subscript on it, equals our initial x position plus our average velocity times the time over which we took our travel. Okay. The other equation, that's our equation for average velocity, another equation for average velocity. Average velocity is equal to your initial velocity plus your final velocity divided by 2. You essentially take half of it. Here's another equation relating our velocity to our acceleration and time. So velocity, our final velocity, is equal to our initial velocity plus acceleration times time. We could rearrange this equation. If you subtract v0 over to the other side, and then you divide both sides by time, you will have the equation that we've already seen. Acceleration is equal to your change in velocity over your change in time. And then we have this equation down here, which relates acceleration, time, velocity, and position, our displacement. So our final x position equals our initial x position plus our initial velocity times time plus 1/2 acceleration times time squared. And then we have a final one here. Our velocity squared, final velocity, equals our initial velocity squared plus 2 times the acceleration times our total displacement. So that's our x final minus our x initial. So utilizing all of these 5 equations, we can solve a lot of really interesting problems. And we are going to practice doing a few of those. But first I want to talk about problem-solving strategies for one-dimensional motion. These are the strategies we will need to use as we're encountering problems in one dimensions, especially using those 5 sets of equations, that set of 5 equations. Okay. So the first step when we're encountering a one-dimensional motion problem is to examine the problem to determine which physical quantities are involved. Okay. Basically read the equation and highlight important points. Our next step is to identify the knowns. Make a list of the things that are given to us in the problem already, or what we can infer based on what we just read about the problem. The next step is identifying the unknowns, the things we don't know. Identify exactly what needs to be determined in the problem. What is the problem asking us to solve for? Step 4, find an equation or a set of equations that can help you solve the problem. That's essentially our set of 5 equations that we just went through, okay? And then we can substitute the knowns into these equations along with their units and obtain our numerical solutions. We want to have our solution complete with units as well. And then we want to ask ourselves, is our answer reasonable? That's why it's important for us to sort of get some physical intuition for what the outcome should be. That's why we talked a little bit already about approximating answers. Does our answer make sense? Is the sign correct if I'm asking you for a velocity or an acceleration? Now we're going to apply that basic set of kinematic equations to solve 2 problems. And the first one is about a car race. We have a race car starting from rest, and it accelerates at a constant rate of 5 meters per second squared.
What is the velocity of the car after it has traveled 100 feet? So the first thing we're going to want to do is draw a diagram. We want to label that diagram and put in our knowns and our unknowns. And so that's what I've done over here. Here I have my car approximated as a rectangle. In its starting position, I'm going to call that position A. And it's starting from rest, so I'm going to say that its initial position, x sub naught or x sub 0, is equal to 0, okay? And it's starting from rest, and also then that means its velocity, its initial velocity, v sub naught or v sub 0 is equal to 0 meters per second. And here we have its acceleration of 5 meters per second squared. Okay, so it's going to travel 100 feet. And we want to figure out what is its velocity when it has traveled 100 feet. Okay, so our unknown in this problem is our velocity here, and all of my knowns so far we've got listed there. Okay, so in order to find the final velocity of our car, we need to consult our equation sheet. So here I have our equation sheet, very handy for us during the semester. And I'm going to look for an equation that has all of these knowns already in that equation, and that the one thing left in that equation that I don't know will be the thing that I'm trying to solve for. V, the final velocity. So when I look here, I see that there's this great equation. We've got v squared minus v sub naught squared equals 2 times our acceleration a times x, that would be its final position, minus x naught, that would be our initial position. Okay, so if we look at this equation, we see that our initial velocity here, we're starting from rest, we know that initial velocity is 0, so I'm going to go ahead and cancel that term out of this equation. Now I'm going to say x equals 0 where my car starts, and so I can cancel out that term right here too, x0, because we're starting from our 0 position here. Okay, I know my x here, final position, that's 100 feet. I know my acceleration over the time, 5 meters per second squared, and I know my, what I'm trying to solve for is the final velocity. Okay, so I'm going to rewrite this equation. We've got v squared is equal to 2 times my acceleration times the final position. So to get rid of this v squared, I'm going to take the square root of both sides. Then I have that v, our final velocity, is equal to the square root of 2 times the acceleration times the final position. Okay, so I'm going to go ahead and fill in those terms now. We've got the square root of 2, or square root of 2 times our acceleration, 5 meters per second squared, times our final position, final distance that we traveled. We see here that it's written in feet, but we're given our acceleration in meters per second squared. So generally in our physics class, we're going to work in SI units, standard units for physics. And instead of feet, we want to convert that over into meters. So let's go ahead and do that now. If I take my 100 feet, I'm going to multiply it by a conversion factor to convert my feet into meters. And so I know that, let's see, my conversion factor in 1 meter, there's 3.28 feet. Okay, and so I'm going to cancel out, we can cancel the units of feet on top and bottom here. And so what I have to do is take 100 times 1 and divide it by 3.28 to give me my distance from 100 feet in meters. And so if I take 100, divide by 3.28, I get that my distance in meters is going to be 30.5 meters. Okay, so this is equal to 30.5 meters. Okay, so I'm going to come over here, and for x, I'm going to place 30.5 meters. All right, so grab your handy calculator, take 2 times 5 times 30.5 meters, and divide and take the square root of all of that term. Okay, now I went ahead and took 2 times 5 times 30.5, and that gives us 305. Now the units here, the units that are inside the square root, those are going to be units of meters squared over seconds squared. Well, we've got a meter over seconds squared times something that has a unit of meter. So if we just think about the units, what we're doing is we're taking meter over second squared times meter over 1. You can do that with anything. And then that gives me units of meters squared over seconds squared. If I square root meters squared over seconds squared, then I get the units of meters per second, which are the units of velocity that we're looking for. So then my velocity is going to be equal to the square root of 305, and that turns out to be 17.5 meters per second. So the final velocity of my car after it's traveled 100 feet is 17.5 meters per second.